the cream mixer specialist. Team 7, are you guys ready?
Yes, sir. Yeah.
7 ready? It's ready, Benny? Whenever you guys are ready.
All right. Ready? All right. Hello, guys. My name is Kevin Francis. This is Edwin Avila, Michael Van Villet, and Robert Moran, and this is our medical device cram. All right. So to give you some background about our device, we went to Sanchez College, the pharmaceutical department, and we wanted senior design ideas. And whenever this lady, the instructor, was giving tours of our facilities, she was giving us ideas, and she mentioned one that stuck out to us, which was the unguator. Now, unguator is a special device that mixes individual specialized cream for individual patients. This is important because you want specialized cream for individual patients so they can get them the type of medicine they need. Now, something that is important about this machine starts off at 1,500, and this doesn't come with any blades. So it already has a high start off to use the device. And this machine can go upwards to 5,500. Some pros about this device, it's already in the market today. If you want to go mix some creams, you can. Some downfalls is that in order to use this machine, you have to buy specialized blades, specialized containers, and specialized adapters. Now these adapters go from $80 and they go higher depending on the size of the container. So as you can see right here, you have a smaller container and it goes higher to a bigger one that's like a mid-level. A downside with this is whenever you're using the blade, you actually have some cream residue. And so the patient isn't getting the full amount of cream they should be getting for what they're paying for. Following, you're also introducing outside elements. So whenever you're taking the device, the container off and putting it into the machine, you're introducing outside elements, and you want to remove that. So that's going into our design of our device. You want to have a means to mix the device without having having to open up the device and having something in there to mix. So we want to have something external to mix it. So we wanted to see if what works. So what we did initially was put Vaseline in a container and shook it up. And as you can see, you get a homogeneous mixture throughout here. So after shaking it for a few seconds, you get a homogeneous mixture, and the food coloring is supposed to represent another medicine. So shaking is a reliable source of mixing. And to talk about design choices, I'm passing to Robert.
Good afternoon, everybody. My name is Robert Moran. And just like Kevin mentioned, we try to make this a bladeless mixture, cost-effective in a short set of time. So we came with 3 designs, which is a rotating discipline pin, a slider, and a crank rocker. To do our final choice, we came with the point system evaluation. So you can see the rotating discipline spin, it was a quick set of time, it allowed different containers. It was not a good distribution on stress, but the part was easy to change. The slider, that was out the thing. So we went with the crank rocker. The crank rocker is a quick set of time, it allowed different containers, it was a good distribution strength, and parts were easily interchangeable. So this is our first design that we came up with. It shows the motion of the crank rocker, the main link, and the holder. And we have well, this is our first prototype. It's my baby. So, as Dr. Garcia knows, I destroy things. So our first stage, you can see in the middle part, our crank rocker, I went over it. So this messed up. So we 3D printed one, and we 3D printed the holder. We tested it with a drill, 3,500 RPMs, and I just went at it. So it broke again in 5 seconds. The good thing, in 5 seconds, it gave us a homogeneous mix. So we already proven that it does work. The only thing is, I broke it in 5 seconds. So just like going at it. So when we learned about testing with a power drill, that there was a lot of vibrations. So what we learned is we added bearings. You may not see it, but we added bearings. We added a heavier base, so it moved, and we added some legs. And instead of a drill, sorry about that. Instead of a drill, we embedded a motor in there with a timing belt. Everything's 3D printed, and for that, everyone is gonna do the process design in more detail.
iteration of design. So, as many of you guys know, iteration drives success. So, in our project, we did a lot of iterations. As you can see right here, we have a lot of parts that we printed out, 3D printed. By changing the length sizes, by testing different motors, different gears, different methods of, like Robert mentioned, timing belt. We even went with gears, also gear ratios, to see if we can get that same torque. We used all these 3D printed parts. Now, one of the things that was iterated many times was a pulley system. Here we have, in the first video, we have the first pulley that we designed. We bought a belt from online. We molded we molded the pulley to the belt that we bought. On that, in the first video, it didn't really grip the belt. On the second video, we went back to SolidWorks, modified the 3D model, and as you can see, it gripped better, but it still had slippage. And on the last one, running at 1500 RPM, we designed it at the specific pitch that we wanted for the pulley to be. And here's our final design. We introduced the timing belt, as you can see, you probably can see better here. We have the timing belt right here with the micro driver stepper and the power supply, cooling fans, so you can cool it down. One of the things that to eliminate from the unguator was processing time, setting up the process. We implemented this locking mechanism, which is simple to use. All you have to do is just press down, lock it, secure the latch, and it's ready to go. You don't need to train a technician on how to switch the blades. Simple as that. That's what we wanted to do. Place it down, lock it, put the latch. Now, we knew that this component will have the most stress, that's going to be applied the most stress to, because it's carrying the container. So we used SolidWorks, we did an FEA analysis. Now, in SolidWorks, there's a feature called fillet, which it does, it connects two surfaces together, as you can see right here, and it creates a small, smooth line. And what we learned from this, that as many of you guys may know, stress is F over A. So the more area, you have more dissipated stress, and that's what we want. Knowing this, we apply this to many of our components, and in fillets here and there, so we can bring that stress down. In our final design test, we used water, white, petrolatum, and ketchup. Ketchup because we're students, we don't have money for creams like that. And we ran the test for about 2 minutes at 1500 RPM. And on both tests, we got 2 homogeneous mixtures. To talk more about the product, the cost, give it to Mike.
All right, so the costs associated with the PLA filament bearings, electrical components, and other purchased parts came in at about $210. All the 3D printed components took about 60 hours to print. So if we're going to mass produce this product, we can't really do 60 hours per model. So we're going to use injection molded parts, and the cost of producing a run of about 1,000 units is about $256 per unit. And so at a retail price of $599.99, it comes in at less than half the cost of the most basic model of unguator that's available. Some future considerations that we need to add that we're considering adding to the design is adding a heating element, which will make it easier to work with refrigerated substances, break down solid gels, and it just makes it overall easier to mix. We wanted to have preset settings for different creams, and you could customize those to just put it on and what type of cream you're making and turn it on, let it go. We want to streamline the locking mechanism, make it a little bit better, a little bit easier to use, and creating a specialized cover for it that locks and preventing anyone from touching any of the components. To conclude, CREM offers a low-cost, easy-operated device that can provide a homogeneous mixture in a short amount of time with minimal setup time, and there's no risk of introducing outside elements or cross-contamination because everything is contained within the vessel when you put the ingredients in. You don't have to mess with blades and trying to feed it through the lid, because it has a specialized lid with a hole in it that you have to feed it through and lock it. It's also, but our machine is also compatible with those same vessels that are used today in the pharmacy with the unguators, and you can just use this machine instead with those same containers, so you don't have to get new containers. And you could really just use any cylindrical container that you have to use. And that's it.
Okay, so this is supposed to be 3D printed cover. The printer broke down, so.
Oh boy, here we go.
That's just a great.
Another thing that we thought was going to do the thing right? Unbelievable.
Turn it on.
Are we gonna see it work?
Unguate me.
Ready, man?
Wait.
I'm so ready.
This guy is the person in charge of destroying everything. Can we put somebody that will keep the things?
Right?
Do we need some safety glasses in the front row?
I signed that for the form before I came in, right? So we have this running about like a minute, but we'll have a homogeneous mix in there. Right now we don't have nothing in there.
We don't have a drive test, nothing.
You got anything? No, but it does work. This is not our cover. We just, last minute just to go over it. Everything's 3D printed. Even the belt is 3D printed. We use Ninja Flex to 3D print it. So, and I think that was the best option, because even the belt that we bought, it was slipping. But this one has good tension and
It all scripts.
everything's 3D printed except for the bolts, the motor, and the bearings, and the bearing place. But I think we did a good job. I'm just helping out.
Let's jump to conclusion.
Well, you were gonna get a 5 until that comment. So.
Take it back.
Reverse.
Good job, y'all. I'm gonna help you out.
I got several questions. So one thing was, have you actually applied it for the purposes of meat?
So in the actual slides, we actually use some of the petrolab, well, it's not petrolab, the actual cream base that they use in the laboratory. So, and we just mix that with food coloring to show that food coloring is supposed to be another type of medicine, and you can clearly see that it's homogeneous mixed around.
Okay, so for the homogeneity, that's my question actually. Because you showed me the positive part. I mean, what is visual? Do you guys do any kind of like mathematical, like basically quantitative analysis? So you just make actually homogeneous or not?
Based off, this will get more clarification. Based off the RPM and how fast the system moves, or
The actual mixture, the product that you get, how do it's actually homogeneous? It might look homogeneous, but is it actually homogeneous? So you can maybe measure the density or something like that to kind of see whether it's even throughout. So do you guys do any kind of quantitative analysis to make sure that it's actually homogeneous?
We have not conducted any tests yet, but we can. I think we will need microscopes. Responsible to determine if it's homogeneous.
One of the things and one of the easiest things to do, especially from the visual part, especially on the medical part, if there was a medicine involved into a white print that is going to distribute a medicine which is going to be visually intangible, then we will need some chemistry to prove the distribution. But based on the same concept of color distribution, you can also have basically from different areas of your print picture, see if the color is identical or in what percentage it differs. And that will actually be in what percentage the medicine or any other product that you're mixing, it will differ. So that's a very good question and something that you need to consider, especially if you guys, like in the previous class, if you guys are trying to go into the medical industry, the level of precision is key. You cannot have 2% in one side and 1.5 in the other. Any other question? Yes, sir.
How does it compare size-wise to your typical ungulator?
So your typical ungulator is about, let's say 2 feet, and so ours, it does have that width, but also with the ungulators, traditional ungulators, you have to clean the blade. So you're right that this may be a little bit bulkier than the ungulator, but in the other aspect for the ungulator, you have to have a device that to clean the blades. Yeah.
What's the max weight in the bar?
The max that we've done was 300 grams. And that was the max that we actually broke. Not into.
Is there any?
How would you compare it to a centrifuge?
A
Or is that
centrifuge?
just completely different?
Oh,
So there is another, instead of the ungulator, it's called the Madisca.
Star.
They use the same process. But that machine cost about $15,000. So we didn't go that route because it has a revolving thing, and then it revolves inside that revolving, and it has a vacuum also with heating elements as well. So our main competition was the ungulator.
I would like to invite y'all to come see the parts and see how majority of these things are 3D printed. In that corner, everyone likes to call it the bag of shame, but it's
All over the 3D printed parts.
So I believe we went through a couple of spools of filament just to get sure that certain locking mechanisms are correct and links are certain lengths correct.
Was that most of the $210?
I would say that we
200.
most of our expenditure went to filament. The motor was way cheaper in comparison to the amount of filament that we use, and everyone
But
places the motor.
yeah, that's just trying to narrow down. Correct design.
There was a question.
I want to make a quick comment. It's on experience in the pharmacy. I can see the practicality of that because whenever we're mixing rash ointments or acne meds or we're doing the constitutions, we shake it. We don't stick anything in there most of the time. But we're not really a compounding
So when we went to San Jack, they were using a drill with the blade, and they were just going like this.
Yeah, we
That's
don't
not
stick
safe at
anything
all, and
inside.
it's-
That only adds
Girls
more
with
to
tools.
the cleaning process and shake, and then you look at it and you can tell it's totally mixed. So I really like that design because it's a lot of what we do. We don't need any utensils.
Thank you. Thank you for that.
So I really like connected that. I know what you're going.
You know where to donate.
Pharmacy?